Hello, everyone. Today we're going to talk about the instantaneous rate of change. So, with instantaneous rate of change, we're going to look at motion along a line, and we're going to talk about the difference between displacement, velocity, speed, acceleration, and even jerk. All right. So let's start by defining displacement. All right. So displacement of an object over the time interval t to t plus delta t. So it's a little tricky. It's a lot of t's there. So t as in time to t plus delta t, meaning t plus. So whatever our interval of time that's changed is, we say the change of s, which is f of t plus delta t, and then minus f of t. So think about it. We have some time interval, and it's how far our object is moving over some time interval. So it looks a little tricky, but all we're saying is how far is the object moving along this line in our given time interval. Okay. Our next one is going to be average velocity. So average velocity, I'm going to write it as v, and then a little subscript of av to say average, is displacement divided by travel time. So we write this as the change in s. So change in s, remember that was from our displacement, over our change in time, which, if we write this out using our other notation, this is t plus delta t minus f of t, and then divided by change in t, so delta t, which kind of looks like our derivative, right? Instantaneous rate of change, we're going to start seeing some connections. So now let's define just velocity. Because average velocity isn't quite the derivative, but velocity is. So velocity is the derivative of position with respect to time. So the velocity at time t, I'm going to say v of t. So I'm going to call displacement, I'm going to call s of t. Velocity, I'm going to call v of t. So v of t, we define as ds dt. So the derivative of s over with respect to the derivative of time is equal to what we had before. But the only difference is now I'm going to take the limit as the change in t goes to 0. So instead of h going to 0, it's change in t going to 0. So now we have our derivative function. So we have f of t plus delta t minus f of t, all divided by r delta t. So when we find velocity, we're not going to use our definition of a derivative, but we can see why we have a derivative and how displacement relates to velocity, because if we break it up piece by piece, we get the derivative function. Okay? Let's keep going. Speed, we're going to define as the absolute value of velocity. Okay? So velocity could be positive and negative, depending on the position of where we're moving. But speed, we just take the absolute value. So we say speed is equal to the absolute value of v of t. So it's the absolute value of ds over dt. Okay? Next, we have acceleration. Acceleration is the derivative of velocity. Okay? So that means we have a of t is equal to dv dt, which is also then imply the second derivative of displacement with respect to time. Okay? Then lastly, we have jerk. We won't talk about jerk too much, but jerk is the derivative of acceleration. And we write it as j of t is equal to dA dt, which would also be the third derivative of our displacement with respect to time. So those are all the definitions we're going to need to be able to look at our examples now. Okay, so let's look at our example. Let's say we have a dynamite blast. Blows a heavy rock straight up. With a launch velocity of 160 feet per second, which is 190 miles an hour, 109 miles per hour. Okay. It reaches a height of s equals 160t minus 16t squared after t seconds. Okay. So we're going to look at some different parts. First, we'll look at A. How high does the rock go? B. We'll look at what are the velocity and speed. So the velocity and speed when 256 feet off the ground. On the way up and down. So I'll reach 256 twice, when we shoot it up and then when it falls down. C, we want to know the acceleration at time t. And then when does the rock hit the ground? let's take this piece by piece. So to start with A. A says, how high does the rock go? Okay. So the rock is at the highest point when velocity is 0. So let's change color so I know I'm using my solution. All right, so we want to know, when is the velocity 0? And we want to know when velocity is 0 because it's going to reach its highest velocity, or reach 0 when it's at its highest point, and then the velocity will switch its sign since it's coming back down. That's why we have the difference between velocity and speed. Okay, so velocity, we take the derivative of our speed function. So if we call our s function, we want to take the dt of our s function, which is 160t minus 16t squared. We take the derivative, and we're going to get 160 minus 32t. So two different power rules there. Okay. Well, we want to know when the velocity is 0, so we can set it equal to 0. So 160 minus 32t equals 0. And if we solve this, I'll let you solve this one on your own. T would be 5. So you can at, subtract the 160 from both sides, divide by minus 32. You get t is equal to 5. So at time t, we want to know that height. So let's find the rock height at t equals 5. So we're going to take that 5 at time 5. We're going to plug it back into our displacement. So we'll call this S max, so displacement max. We just found happens at 5. So we're finding that time value for velocity 0 to plug it back into our original function to find our displacement. So we know it happens now at time 5, but we want to actually find that height. So minus 16 to the 5th squared. So you can go ahead and plug that in. That should give us 660 times 5 is 800. 16 times 5 squared, so 16 times 25 is 400. So this would be 400 feet. And that would be our displacement. So this is a little tricky one because we have to find the velocity at time 0 to see when it achieves the highest point, but then we have to go back and actually find that height. So we find the time first, then we can go back and we plug it into displacement and we see how high that rock goes. Okay. Part B now. We want to find at 256 feet off the ground, what is the velocity? Okay. So what we want to do first is look at our displacement. So we have 160t minus 16t squared. And we want to know when it's equal to 256. So we want to find the rock's velocity at 256 feet. So we take our displacement first. We can do a little algebra here. So we want to probably subtract that 256 to the other side. So I have 160t minus 16t squared minus 256 equals 0. I could factor out a 16. Let's rewrite this in a little better order. So I have t squared. Let's take out minus 16, so we have positive. So I have t squared, and then I have minus 10t, and then I'm going to have plus 16 equals 0. We can go ahead and should be able to factor that one. And I'll let you factor it or plug it into the quadratic formula on your own, but we should get two solutions of 2 and 8. So now we know the two times again. So again, we're finding time first, but we have the highest, the point we're looking, not highest, the point we're looking for here. So we can find the time that way. But now we're looking for the velocity. So we plug those into the velocity function. So I want to find velocity at 2, and I want to find velocity after that at 8. So we can plug in v of 2. So we have 160 minus 32 times 2. So in the last part, we found the velocity function. That's where I'm getting these numbers. So if we do 160 minus 64, we should get 96 feet per second. And with velocity, remember, it's going to be feet over seconds because I'm taking the displacement over time, so feet over seconds. Then if we want to find v of 8, we go back to our velocity function and plug that in. Remember, velocity is from the last question we found was 160 minus 32t. If I plug in 8 this time, I should get minus 96 feet per second. Okay? So that makes the speed very easily. The speed, we take the absolute value of them, so the speed is going to be 96 feet per second. Okay. Is that all we need for this part? Okay. Yep, we can move on to C now. So we want to find acceleration at time t. So remember our velocity was 160 minus 32t. So we want to find v prime of t, which will be straightforward. It'd be minus 32. And we want to make sure we have our right units, feet per second squared. So at all times, gravity remains the same. So the force is just different in different directions. So gravity is going to have the same force the entire time of minus 32 feet per second squared here. So when we take that derivative of velocity, v prime of t, remember it's also a of t, so our acceleration is always minus 32 feet per second squared. Okay, and that's just because gravity remains the same, so that's why we have a constant value there. So now we can move on to D. When does the rock hit the ground? Right? So let's go to our velocity question. So remember we looked when velocity is 0, the first one. It's going to be similar, but instead we want displacement this time to be 0. So same steps we're going to do for when we found velocity equals 0. We just want displacement equals 0 because we want to find when with the time for which it hits the ground. So let's look at our displacement again, which was what, 160t minus 16t squared. And this is our displacement. Okay. We're going to set it equal to 0 though. So let's set it equal to 0. Okay. Again, we can factor out. Let's factor out 16t. If I factor out 16t, I'm left with 10 minus t. So we get t is equal to 0 and t is equal to 10. So our answer would be t equals 10 because we know it's on the ground at 0 because that's when we blasted it. So at the point of blast, of course, it's on the ground. But when we have our second value, that would be when it hits the ground again. Okay. So that's going to be it for today on instantaneous rate of change. please go ahead and try those practice problems for these. And I'll see everyone next class, and I hope everyone has a great day.